All right, good morning, everybody. Thank you also very much for coming this morning to what it is, the inaugural Distinguished Lecture Series speaker for this new series that we have started out of the Vice President for Research and Partnerships Office. For those of you that don't know me, my name is Tomás Díaz de la Rubia. I'm the new Vice President for Research and Partnerships here at the university. It's been a fabulous 6 weeks so far. Busy, but really interesting. I have met a lot of you here in the room, not everybody yet, but hopefully I will soon, and have been learning a lot about just the outstanding work that is already going on at the university, and really talking broadly with faculty and leadership on campus about how do we go to the next level? How do we take our game and become number one globally in research in areas that are relevant to our strengths and to the key strategic areas in which we have a strong footprint around the world. So that's our ambition, and with all of us and all of you together, I know we're going to get there. And part of that, for me, was having the opportunity to hear from really distinguished members of the academy and of the research world that are doing leading-edge research in areas that are, again, relevant to us. And so that's why we launched this new Distinguished Lecture Series. If you saw the announcement that came out about a week or 10 days ago about this, I solicited input from everybody across campus for names that we can invite to this particular lecture series. Our plan is to do 3 or 4 of these per semester. I think if we do 3 per semester, we'll be doing great. We'll invite the speakers and make, an agenda like we did with Vlad Shalaev and Sasha Boltaseva this week that cuts across the entire campus. So again, part of my goal with this is to invite speakers that can talk to us broadly about topics away and outside of the traditional disciplinary boundaries of a particular specific department of college, but rather to talk about the impact of the research on society in a broader sort of way. So with that, let me introduce to you Vladimir Shalaev. I don't have any notes with me, but all I have to tell you is that Vlad is just a global superstar. Vlad is a distinguished professor of electrical and computer engineering at Purdue University. And, he has been creating new fields his entire career. He was a pioneer in proposing the idea behind Metamaterials. And ever since he joined Purdue after that, he's been the pioneer in really recognizing and launching forward what is today the new phase, a very, very exciting world of where quantum information science and technology is going to take us into the future. He's a visionary. I've had the pleasure of knowing him now for about 5 years since I first went to Purdue. And every time he's ahead of the pack. He's thinking about what's next, what's coming down the pike, what is going to transform the way we do research down the road, what are the really exciting new areas that we need to focus on. His scientific productivity is out of scale and commensurate with his impact that he has had in the field of physics and engineering and electrical engineering in general. He's just to give you a data point, his citation number is in 45,000 or 48,000 or some astronomical number like that, with papers that really, truly have, it's not just about publishing 1,000 papers, it's about publishing papers that have had a big impact on the community. And he has been doing that for many, many years and continues to do that with his group at Purdue University. So with that, I introduce Professor Vladimir Shalaev, who is going to talk to us today about how plasmonic metamaterials meet quantum going forward into the future. Vlad?
Thank you, Thomas. When Thomas invited us, we are looking forward. And I know that any place Thomas goes, you should expect big transformative changes. And I clearly could see that this atmosphere within a day and a half, like everybody expects something big coming, some huge changes coming. That's the spirit that Thomas brings into any place he goes. And in my memory, the best thing what happened to Purdue is Thomas. I mean, what he did to Discovery Park. So expect big changes, but he would not do it for you. You should do it with him. Build up the vision and become the best in the areas where you have already some strengths. And going to quantum and AI, that's what Thomas pushes for, and I think that's fantastic. That's where the next technology evolution is happening. And actually, part of my presentation is going to be about this. We ourselves, actually, we're working in the area of metamaterials, and yes, we could say that we are pioneered many things in that area. We have many firsts in the area of metamaterials, which are artificially designed and engineered materials. Meta in Greek means beyond. Basically, with these materials, you get properties which you cannot accomplish with materials existing in nature. But we now think how to bring it to quantum and how actually it could make a difference for the quantum field. This line of thinking might be useful for you guys too. Think where you already have existing strengths and how to bring it to the next technology evolution, which is quantum and AI. So this is the topics I'll try to cover today. I'll start with remarkable nonlinear optics, which could be accomplished by combining metasurfaces and metasurfaces 2D version of metamaterials with materials that have epsilon dielectric permittivity close to 0. So it's very unusual. It's kind of singular optics happening in this case. And you have remarkably enhanced nonlinear optical properties in that case, which could enable what we call four-dimensional photonics, or in other words, space-time photonics, when you control light not only in space dimension, that's what metasurfaces do, but also in time dimension. By taking the idea of metasurfaces to yet another degree of freedom, to the frequency domain, it turns out that you could realize really important applications. This is just paper came out a few weeks ago in Science, and we just showed many orders of magnitude faster beam steering that has been done before, which could actually be quite important for autonomous vehicles as optical lidars. And it's amazingly simple technology proposed by my student who then moved to Stanford. And I will show about this. And this is based on the idea of metasurfaces in frequency domain. This is the main focus of our research now. We basically are suggesting new unorthodox approach to use plasmonic metamaterials to dramatically speed up quantum processes. Why it's important? Because the stumbling block for quantum applications is so-called decoherence. I mean, the advantages of quantum, because you have this quantum superposition, which is very fragile. It's very hard to keep this quantum superposition. That's what behind quantum speed up. That's behind of quantum supremacy. But how to deal with quantum decoherence, which very quickly breaks this superposition. So our simple idea is don't try to keep it. Don't try to make it longer. It's too hard to do. Just speed up your processes. Make them happen before quantum decoherence happens. And it looks like plasmonic metamaterials, the area we have been working for the last decade, could make a difference, could actually make this happen. And again, this is the line of thinking it's trying to encourage you to do the same type of things. Like, I have a strength in certain area, how I could bring it to a new area. So that's we are very much focused on about. Yet another thing which is along the lines what I hope will be happening here, it's to use the AI. And in this case, I show that the AI combined with quantum makes a miracle. And actually, I'm not aware much of work in this area, maybe 1, 2. And we already show that it's not just small change. It really enables absolutely new things if you combine AI with quantum measurements. And finally, I also show something which is deep in the heart of physics. It's so-called topological insulators, how you also could combine it with the idea of quantum and make new things for quantum information systems. All right, that's the ambitious, the ambitious contents, table of contents, which I would like to cover. Let's start with metasurfaces. to me, I mean, I'm trained in physics, in theoretical physics, and the most beautiful part about physics when say everybody who got education in Russia in theoretical physics, we actually, the book, it's implied the Landau's text, the series of books. And the most beautiful thing about these textbooks, in my opinion, it's the connection between symmetry and conservation laws. It's really beautiful how you could just look at the symmetry, write down Hamiltonian, and then develop all the equations describing the physics behind. It turns out the very first person who connected the two things, symmetry and conservation laws, was this German mathematician, Emmy Noether. And it was done more than a century ago. She actually mathematically proved that there is this connection. If you have particular symmetry, then it results in certain conservation law. Like, for example, in the case of this, if you have translational symmetry, then your momentum should be conserved. And because of that, when light is incident into interface between two different materials with different refractive index, the transverse component of momentum should be conserved. And if refractive index is higher here, to have this conservation of momentum, light has to bend toward the normal. That's the idea behind this Fresnel's law. It's a very simple consequence of the momentum conservation, which is in turn follows from the translation symmetry. And because of the temporal symmetry, you have the fact that photon energy should be conserved. The frequency in the first minimum should be equal to the frequency in the second minimum. Of course, h bar omega gives you the energy. And I will show how as metasurfaces you break both these conservation laws, the momentum conservation law and the energy conservation law. And that's why it's beautiful, that's why it's powerful, that's why actually it's opened up new technology driven by large now by my friend Federico Capassa, which is called flat optics, optics which is based on exceptionally thin optical elements. And the idea behind is, let's place an array of antennas on top of this interface. Antenna could be much smaller than the wavelengths. But when it couples to light, it abruptly shifts the phase, because this is resonant interaction. And if now my antennas are different, like it's shown here in shape, like let's say this angle is different between the two arms of antenna, then the shift of phase would be different. That means that the phase required because of the coupling of light with antenna in this point would be different from that point, So you have gradient of phase along the interface. But gradient of phase along the interface means momentum. So dphi over dx means that momentum. So you bring additional momentum. And because of that, you break in photon momentum conservation. As a result, depending on how you design these antennas, you could send your light in any direction. You could break this Fresnel's law. Basically, you have to introduce so-called generalized Snell's law, which takes into account momentum introduced by this metasurface, which is ultra thin, much thinner than the wavelengths. So as opposed to the conventional bulk optics, where you have this accumulation of phase when light propagates, and it takes, of course, many wavelengths to accumulate a significant phase, here you do it abruptly. So it's a nice idea, and this is an example when science and technology come together. Beautiful science idea related to symmetry conservation law actually now enables a whole new field in the optical technology. Microscope, lenses, holograms, they all now are doing this, making them ultra thin. And so there are many, many big companies now interested in this technology. So now I'd like to combine this idea of metasurface with new materials. Yet another thing I learned during my research career, there are so many ideas, they stay in line. What makes a difference is new material, new fabrication approach. Look always for materials. And at some point, I found myself that I pretty much doing material science, even though I never was trained in this. And Sasha, actually, my colleague and beloved wife, leads this effort. And we are always looking for new materials. So in that regard, materials, when they cross to point where epsilon goes through zero, that's really some miracle happens. Let's think of this. Maybe I will start with the standard textbook formula to illustrate the beauty of this E and Z material, epsilon near zero materials. This textbook formula, which tells that refractive index, which actually tells how phase propagates in a material, is a linear refractive index, a characteristic of any material, a nonlinear one, the so-called Kerr effect. And I teach this nonlinear optics, I don't know, for decades, and I never paid attention myself to this, that this nonlinear term, which is proportional to intensity, of course, it depends on the nonlinear susceptibility, chi3. This is a chi3 process, but it has linear refractive index in the denominator. So linear refractive index is square root of epsilon times mu. If my dielectric permittivity goes to 0, then refractive index goes to 0. And then you have quite unusual situation. The linear term, which is always dominates, nonlinear term is small. It provides these small nonlinear corrections. Actually, linear term goes to 0, so that nonlinear terms is larger than linear one. The whole perturbation theory stops working. And moreover, this nonlinear term is enhanced because linear refractive index is small. This is what I call a new branch of nonlinear optics, when you have enhancement of nonlinear response because linear index becomes small. So, and sure enough, there are such materials, and that's what Sasha actually developed, so-called transparent conducting oxides, and specifically aluminum doped zinc oxide. We visited to the ECE. I know there's some activities related to zinc oxide. If you dope it with aluminum, and depending on how much you put this metal into this, you could have this crossing point where epsilon goes from positive values when it's dielectric to negative values when it's metal. At any point you want. It simply depends on the doping. And that includes the very important telecommunication wavelength, 1.3, 1.5. Actually, it's up to us. We could design it. And look what's happened with A0. Epsilon goes to 0, and the imaginary part is very small. It means that the refractive index, which is, again, the square root of epsilon, actually becomes very small. And that's what we observe when we measure this N2 nonlinear term as a function of the wavelengths. At the point where epsilon crosses 0, at the point where linear refractive index becomes small, my nonlinear response jumps up. So this is low index enhanced nonlinear response. And to bring into this some understanding, you should realize that when you cross 0, basically you go from positive epsilon from dielectric to negative epsilon metal. You have metal dielectric, metal insulator transition. So you dramatically change your optical properties. And anything is huge compared to 0. And our reference point is here 0. If I slightly increase charge carrier density, my material becomes metal. If I slightly decrease, it becomes dielectric. Clearly, I change dramatically optical properties, but it doesn't take too much change in charge carrier density because I compare to the 0 point. So delta n, which is this delta n, relative to n naught linear refractive index is remarkably large here. It's actually unparalleled large. And it's true not only about this particular effect, it's true about whole nonlinear responses. It's really like new branch in nonlinear optics, which was enabled by these materials. And so what we obtained is nonlinear term, in this case, 5 times higher than linear term. Actually, in later experiments, we showed 100 times higher than linear terms. This is hard to imagine. I mean, you never have it with conventional materials. Nonlinear terms, not just, let's say, significant. We say significant when it's 0.1%. It's actually 100 times larger than linear one. So, and I should admit, actually, there is no theory for this. It requires development of entirely new theory. You could ask, what was the physics behind this? Why you have all this dramatic change? There are 2 things. First of all, I should admit there is no complete understanding, but there are some guiding ideas. First one, the dielectric, the displacement current D, which is epsilon times E, the normal component should be continuous across the interface. Okay, if, let's say I go from air to material, in air epsilon is equal 1. In my material, epsilon is close to 0. But epsilon E should be continuous. So if epsilon goes to 0, the local field gets dramatically enhanced. So you have this confinement induced by the fact that epsilon goes to 0. You have field enhancement because epsilon goes to 0. This is one point. Another point, we should realize that we're dealing with highly singular optics. When the refractive index goes to 0, my phase velocity diverges. It means that the phase propagates with infinite speed. And the wavelength also diverges. It means that the coherence now becomes macroscopical because wavelength is wavelengths in vacuum divided by refractive index. If it goes to 0, the wavelength becomes macroscopic. And the group velocity goes to 0 as well. So in this case, it means that you're dealing with very slow light. It's also enhancement coming from slow light. Really highly remarkable physics behind this. And what is important is not only huge nonlinear response, it's very fast. It happens on the scale of 100 femtosecond. Because when it comes down to optics, we say that optics is as I like to say, the best electronics is called photonics, because optics is much faster than electronics. And so whatever you do with photonics, you should demonstrate the speed, because speed, that's actually what makes photonics advantageous when you compare it versus electronics. And here it's 100 femtosecond. Remarkable change when the refractive index changes by 100%, when transmittance, reflectance change by 100%, and it happens within 100 femtosecond. It, of course, opens up possibilities for modulation, switches. It's a remarkably strong effect. So, and we also demonstrated for other effects, not only for Kerr effect. In this case, it's so-called time reversal, which is kind of interesting physics. So it was first suggested by John Pendry from Imperial College, who said if you take a very thin layer of material, which is where the electric permittivity modulated at frequency 2 omega through nonlinear process. And if a beam at frequency omega is incident in such a material modulated at 2 omega, then because of 4-wave process, you have omega minus 2 omega, which is equal minus omega, but getting negative frequency is equivalent like getting inversion in time domain. So this process works as time reversal process. So the only requirement that the fin should be much smaller than the wavelengths. So when you send the beam at omega, because of this 4-wave mixing process, what happens, you would get the beam which propagates in the opposite direction, phase conjugated beam so-called, and a beam which propagates in the direction corresponding to negative refraction. Both beams correspond to this time reversal process. It's a nonlinear cool process, interesting in many regards, and there was some experimental demonstration there, but in all cases, the efficiency demonstrated was below 0.1%. We took the same process, but we took this aluminum doped oxide, which Sasha makes, and we took it to the spectral range where refractive index goes to 0, or very small. And you could see that the efficiency for this process has linear refractive index in the denominator to the power 4. In the previous case, it was Kerr effect. This is 4-way mixing effect. And you have the refractive index going to the power 4. It should be dramatically enhanced. So what we obtain is actually 100% conversion efficiency. It could go even beyond 100%. You shouldn't be surprised to this because you take energy from the pump. So the point here, this low index enhanced nonlinear optics, it's pretty much a new branch in nonlinear optics, and it's true for many optical processes. So, but we took it to yet another level. If you're an engineer, if you actually could notice something, wait, when epsilon goes to 0, yes, the field increases dramatically, but epsilon meaning close to 0 means that you have huge impedance mismatch. So all the energy would be reflected because of impedance mismatch. How to get energy inside of your material? Yes, it's enhanced, but how to get it inside of such a material? So for that, we place this metasurface on top of this, which is an array of antennas. And what antennas do, they actually couple to this ENZ material. And because of this coupling, which actually turns out to be strong coupling, the energy very efficiently coupled into this material where you have all this dramatic enhancement. The problem could be described by these two coupled oscillators. One oscillator representing ENZ mode, another oscillator representing this resonant frequency for my antennas. And this is actually a very simple model which fits nicely experimental data. And you have this typical splitting, which is a feature of coupling. And this splitting actually larger than the decay constant for both antennas and ENZ mode, meaning that this is a strong coupling. And what we obtain is 15,000 enhancement of nonlinear response compared to bare ENZ material. So ENZ material already great, but it's hard to get energy inside. By combining it with metasurface, we have 15,000 further increase in enhancement in nonlinear response. We are actually working with so thin layers, like 30 or 40 nanometers, and can really get very dramatic nonlinear responses. So this is an example how new physics, in this case, singular optics related to ENZ, combined with new materials, enables really cool new phenomena with potentially important applications. So let me move from conventional metasurfaces, which I already mentioned because of the shift in phase which depends on the position. You introduce momentum and you break photon momentum. Now we have materials that could modulate properties in time domain in a very fast fashion. So that allows you to introduce what we call space-time metasurface, where you control light not only on X, Y, Z, but also in time domain. And then I take it to this frequency domain. Oh, by the way, things in quantum happen so fast. Everything what I'm talking about today, it's actually published this year or not even published yet. So it's very brand new stuff. And that's another exciting thing about this research, that we keep opening new and new stuff. So let's come back to these metasurfaces. As I pointed out, because additional momentum introduced by metasurface, you have this, you break the photon momentum conservation. As a result of this, let's say beam, when it's incident on this metasurface, wouldn't be reflected in this direction, which is normal Fresnel's law dictated, but would go to some other direction depending on this delta K. So that's because you introduce gradient of phase in space domain. But in this case, you don't break reciprocity, right? There is no way to break, there is no reason to break reciprocity. There is Lorentz theorem for this, which tells us that you have to have magnetic field or nonlinearity or modulation in time to break reciprocity. And the reciprocity, I compared photonics against electronics, but the holy grail about for photonics is to have this non-reciprocity, light diode type of action. Then you could think of controlling light in a similar way you do it with electrons. So it's very important to have this non-reciprocity, which is easy to do with electrons. So for that, what we do, we modulate now metasurface not in space, but in time domain. By using materials which I was talking about, you could have this very fast modulation. For example, optically pumping them and electrically pumping, you change the electric permittivity in time domain. Now it varies not in space domain, but in time domain. What would happen in this case? Let's say if I have a light at frequency omega. This is either frequency surface corresponding to that frequency incident on such time-varying metasurface. Because of modulation in time domain of material properties, the frequency would be shifted. So this is like a Doppler shift. So you have this modulation in time. Gradient of phase in time domain means frequency. Similar like gradient of phase in space domain means momentum. Gradient of phase in time domain means frequency. So you have this Doppler shift. So as a result, after coupling to this metasurface, the frequency of light would be changed. So my new either frequency surfaces would be different. Let's say my red light becomes green light. So then when I send it back, it again would be experiencing the same shift in frequency. So then my green light would become blue. So I shift the frequency. And in this case, of course, it would be non-reciprocal because we change the frequency. So light starts from here, goes here, comes back, and goes to here. So I break reciprocity. This is non-reciprocal light. This is light diode, which, as I said, is very important for practical applications. And of course, what you do in this case, you break photon energy conservation by introducing the shift of frequency coming from this time-varying metasurface. So this is, I think, a very powerful idea. And my former student actually did experiment. It should be published soon, exactly on this idea. The idea comes from our group, but my former student, who is now in Penn State, did experiment. So, but we also would like to take this idea to yet another domain. Many of you heard of photonic crystals. That's something what expected to completely change the technology. It didn't happen so. Not any great idea results in great technology, but photonic crystals actually did result, for example, in photonic crystal fibers, some important applications, perhaps not as much as we expected, but some important ones. But physics is beautiful. So with photonic crystals, what we have the electric permittivity periodically modulated in space. And similar to conventional crystals, when you have periodically arranged lattice ions, electrons, you have these electron bands. In this case, you have periodically arranged the electric permittivity, and because of this, you have photonic band gaps. And because of photonic band gaps, you could have this tiny, very efficient cavities, microcavities as just a defect in photonic crystals, or waveguides, lots of exciting things. But there is a space-time duality in Maxwell's equations. So what if I now modulate the electric permittivity not in space domain, as in the case of photonic crystals, but in time domain, like it's shown here? Then I'm talking about photonic time crystals. Why? Because in this case, because of the space-time duality of Maxwell's equation, my modulation in time domain would mean that I would have band gaps not in energy space, like in the case of conventional photonic crystals, but in momentum space. But that's very interesting. Now I have, for momentum space, for k vector, I have certain band gaps. This is a brand new idea, and I'm working with my friend from, Sasha and myself, working with our friend Moti Sege from Technion in Israel, to develop new type of topological insulators based on this. It's something which hopefully will come soon out. But this is just to illustrate when with good materials, good ideas, you really could come up with something brand new. So yet another idea. I already took this idea of metasurfaces from space domain, where you break photon momentum conservation, to time domain, where you break photon energy conservation. Let's take now it to frequency domain. So the idea to have a gradient of your properties in space, in time, what about if I have gradient in frequency domain? So let's be specific. Let's talk about this beam steering thing. For that, you normally use array of antennas. It's a well-known technique, and these autonomous vehicles, LiDARs use this actively. But the thing about this approach is that the way you do it, you have every single antenna the same frequency, and you control the relevant phase between different antennas by modulating it. Phase. So you could modulate it by using electro-optical modulators, some liquid crystals, gate-tunable metasurfaces, but the speed with which you could modulate the relative phase between antennas, it's microsecond at best. You cannot do it faster. So it means that your beam steering not going to go faster than microsecond. So, and when I change the phase, I change the direction where constructive interference for waves coming from different point sources occurs. Let's say now it's in this direction. If I change the relative phase, it would go in some other direction. That's the way to do beam steering. Okay, let's completely change the thinking. Let's do it in a different way. What if I lock the phase of all these antennas in the same, but instead of that, I make frequency of these antennas different in a way that the separation, the difference in frequency is the same, and they especially separate them. Think of a frequency comb. One big thing which brought dramatic change into optics, resulted in Nobel Prizes, is frequency comb. It's a huge thing. So you have this locked in phase different frequency spectral components, but they all occur in the same special point. What I take different spectral components and specially separate them. The lowest frequency I place here, the larger frequency here, the other frequency here, the yet another frequency here. I just specially separate my different spectral components. That's what is shown here. What would happen in this case? It's so simple idea. Actually, I could not believe that nobody did it. We checked all the literature. It turns out no. But it's probably the simplest thing we ever did, and it looks fantastically, actually. So you have this antenna, what we call frequency antenna, which separated in frequency by roughly, let's say, 100 gigahertz, and specially arranged in periodical fashion like it's shown here. Let's say initially my constructive interference occurs in this direction, but because frequency here is higher, the phase propagates faster. Phase is omega t, faster than here. Here, the phase propagates faster than here. So next time, the light would bend in this direction, then in this direction, and the time period with which it would change the direction of constructive interference is just related to this separation in frequency, which could be picosecond time. It's a million times faster. And all you do, you just specially separate these different spectral components of your frequency comb. This is the way it works like. You see, it's with picosecond time. It swaps over huge, large area. And that's actually could be very interesting for sensing application, for printing, for autonomous vehicles, optical LiDARs. And it doesn't require any energy as opposed to here. Here you have to energy to modulate it. Here it happens by itself. It's just interference. No any source of energy is needed for this. I mean, the idea is so simple. We certainly should be able to demonstrate it. But first, let's address the question, why it's curved. Did you ever heard of beam steering where beam actually curved? We have this idea that light propagates along a straight line. No, actually. So the truth is, it is curved. It's not exception, it's a rule. The reason for that is just when time of angular steering, which is 10 picosecond in this case, is comparable to the propagation time, Then you have the situation similar to curved water stream when you rotate fast a water hose. This droplet of water, which you could think of photons, would be curved. So let's say within 10 picosecond, light propagates for 3 millimeter. That's my photons here. In 10 picosecond, because it rotates so fast, my photons would be already here. They always propagate along straight line, but still it occurs so fast that you have this curving effect. And it always occurs, you don't see it at the lower speed. So when my student moved to Stanford as a postdoc to work with Mark van Gersma, they did this experiment there. And I mean, it's, as I said, it's so easy. You take frequency comb. You want to specially separate them. What's the easiest way to do it? Take diffraction grating. I mean, depending on frequency, different frequency components that go in different direction. Then you focus them. This is not actual frequency array of antennas. It's virtual frequency array of antennas because nothing physically sits here. But you have frequency here. The smallest here is higher. Here is the highest one. You specially separate frequency component. This is my frequency array. This is trivial, simplest way, but this is old-fashioned way because it requires this standard bulk optics, diffraction grating, and the lens. We are now working in the era of metasurface. Instead of diffraction grating, I could make metasurface, which could be much smaller than the wavelength, but acts exactly the same fashion as diffraction grating. I could take another metasurface, which would act as a lens and could be 10 nanometers in thickness, but do the same focusing effect. But because it's purely linear effect, I could combine the two and make one metasurface, which does both functions, grating and lens. And that's exactly what we did. It's silicon-based metasurface, properly designed. Nothing special about this. Could be fabricated in any place. So you could see it here. So we have this frequency comb. We sent it to this metasurface, frequency array metasurface. You have this array of antennas, virtual array of antennas, different frequency, specially separated. And then you measure it by using this streak camera. And we could see that within 10 picosecond, the angle changes from -15 to +15. So it's absolutely much faster beam steering than anything demonstrated so far. And it became possible because we took this idea of metasurfaces first from space domain to time domain, then to frequency domain. All right, the next challenge to accomplish, okay, we got used to this. With metamaterials, you do miracles. You completely transform the conventional optics. So now we have this quantum challenge. What metamaterials, in this case specifically plasmonic metamaterials, could do for the quantum? That was the line of our thinking. So I hired Semyon Bogdanov, who at that time did actually know any quantum. And I said, hey, your challenge, learn what we do in metamaterials and find out the area where it would be completely transformative for quantum, what metamaterials could do for quantum. And that's eventually what we came with. It was just, again, published a few weeks ago. We suggested the way to speed up quantum processes to the extent that they outpace the decoherence rate. And because of that, they become immune to decoherence because they happen just faster than decoherence. So coming to quantum, it's actually not clear which material platform eventually would be winning. So you know that there are a number of groups pursuing very different directions for all quantum information systems. And they clearly trade off between the interaction strength, where superconducting qubits probably provide better performance, and coherence, where actually photons provide better protections. And they, in all between these trapped ion, color centers, and all other approaches. So in Purdue, we're trying to pursue all the directions. We are big. We could accommodate this. It's not clear which would win in the end. And the truth is probably these different material platforms would find their own niche. But just to emphasize that the problem is not trivial. You need to have interaction strengths from one side, but you also need to have good control, good coherence. If you look at what is best so far accomplished in the area of quantum communication, arguably this Chinese experiment. And I'm sitting in the European Research Council panel. I could say that unfortunately, this country lacks not only Europe, but particularly China. China is the leader in the area of quantum. That's the truth which we have to deal with because it's so strategically important, the quantum area, so we really don't want to be second to any other country. So what Chinese did, they used this communication through satellite, and what they showed is the rate of this quantum communication is 10 kilohertz. But think of this 10 kilohertz in optics. Remember I told you that optics, I mean, it has to be terahertz. That's where all the advantage comes. And the reason for that is actually small light matter coupling. One of the biggest advantage of photonics, photons, they are robust. They don't interact with each other as opposed to electrons. They don't have charges. And the interaction with matter is very small. Therefore, they are robust. Therefore, you have this coherence. But on the other hand, this is a double-edged sword. You want to have this coherence, but you also would like to control photons. You want to generate them. You want to reroute them. You want to switch them. For that, you need strong light matter coupling. So how to do it? So the challenge here is to increase light matter coupling when it is needed. And when you send information from one point to another one, take the full advantage of their robustness. So you have to be able to switch on light matter coupling, make it strong, or switch it off and let photons keep the coherence. And the way to increase light matter coupling is well known. This is Purcell effect. By the way, the graduate of Purdue. And his famous paper where he introduced this Purcell enhancement is the shortest paper I ever read in physical review. It's one paragraph. That's the length of the whole paper written by Purcell, which actually still has truly dramatic impact on so many areas. So the Purcell enhancement, the idea is simple. If you have a quantum species and an emitter, for example, if you would like to increase coupling of that quantum emitter to light, put it in a cavity. Then photon would travel many times and would have many opportunities to couple to your quantum unit. So this is a standard way to increase light matter coupling, and it's proportional to the ratio of quality factor of your cavity. Not surprisingly, the higher the Q, the more times photons would hit the atom, and inversely proportional to the volume where light is confined. And most of the group, if not all of them, pursue the direction to control this light matter coupling by using dielectric cavities, for example, photonic crystal based cavities, as I mentioned before, with very high Q. And Q could be really high, million or 100 million, but volume is limited by diffraction limit, lambda cube. So you do have dramatic enhancement, but you face the same problem. Think of this, as particularly engineers, we know it very well. The higher the quality factor of your resonating system, the slower the response, right? That's why, I mean, if Q is huge, then the response, the width, the spectral, the bandwidth would be very narrow, and the time of response would be very slow. But the idea is exactly the opposite. We want to have it fast, faster than decoherence. So what we propose is to go the other way around. Let's use materials with small q, like plasmonic materials. Plasmonic materials is basically metallic-like structures which have these free electrons oscillating between the boundaries of your nanostructure. And quality factor for plasmonic structure is typically like 100, okay? Which means that in this case, the bandwidth would be huge, which is good. The response time would be fast. If, let's say, my quality factor of 100, the optical frequency, let's say, around 1 micron, or let's say a femtosecond, you take quality factor of 100, it means the response time in the range of terahertz, 10 terahertz. That would be the response time, very fast. But you need to get the same high ratio. How to do it? The volume. What is unique about plasmonics, plasmonics confine electromagnetic energy into exceptionally small areas, like 5 nanometers. 5 nanometers is 100 times smaller than the wavelengths in the visible, 500 nanometers. You should take it to the power 3 because it's volume. It's 1,000,000 times enhancement just because of the confinement. Plus Q could be 100, it's 10 to the 8. It's same strong Purcell enhancement, but Q is small, and therefore the system is fast in broadband. Now we're talking. Now we could take advantage by doing the processes faster than decoherence. That was the idea generated in our group, and actually, as I said, it was just published a few weeks ago in Science. So that's the illustration that's taken from that paper. So the typical approach which all groups pursue, they go all the extremes to increase the coherence time. They trap atoms, they trap ions, they go to low pressure, they go to exceptionally low temperatures, so the decoherence time increases. And I'm showing here for the example of generating photons. Let's say if you would like to generate single photon, this is just like one specific process important for quantum information system. If you would like to have it coherent, indistinguishable photons, it means that the coherence time should be longer than the time within which your photon emitted, so there wouldn't be any change in phase. But what I'm saying, let's decoherence to be the way it is. Let's just do faster emission of photons, so that during the time when photon emitted, no decoherence happened. And I do this speed up through this plasmonic speed up, through the exceptional confinement of light in exceptionally small volumes, without sacrificing the speed, because my Q is modest, not too high. So well, we started to work in this direction, and I first show you some preliminary experiments. It was kind of naive. Now we're taking to the next stage. But we're using for this antenna. We're talking quite a bit today with my colleagues in ECE today about antennas. Antennas are important. So what is the trick here? We use so-called gap plasmons. Gap plasmons excitations occur between two metallic structures in the dielectric gap. And in this case, electromagnetic energy is confined within this gap, which could be very small, as I pointed out. So we use this epitaxial silver film, and we use this relatively large silver antenna. By large, I mean like 100 nanometers. Whereas the gap itself is like on the scale of 10 nanometers. So because of this strong confinement, you have this very strong enhancement in nonlinear, in inline metacoupling. But you need to outcouple these single photons coming, for example, from nitrogen vacancy in nanodiamond very fast before decoherence happens. For that, you need really efficient antenna, relatively large antenna. So strong increase in light metacoupling because of these gap plasmons, and very fast outcoupling because of this nanopatch antenna. So, and then the trick, then it works. So that's the first results we obtained. So to prove that we are dealing with single photon generation, we do this correlation function measurement, the G2 function. This is standard way. And what we obtained at the room temperature, we first randomly distribute these nanodiamonds on silver film, then randomly distribute these cubes. In some cases, just accidentally, cube sits atop of this nanodiamond. And we see that like 30 million counts per second, which is the highest rate of emission of single photons at room temperature observed so far. If I take into account that the efficiency of photodetector is 70%, the collection angle is 50%, and the transmission of all optics use is 25%, the actual amount of photons emitted is 500 million single photons per second, which is a very huge number. But this is far from being optimized. What we are doing now is a precise deterministic assembling of these antennas. Basically, we pre-select this efficient single photon emitters based on nitrogen vacancy in nanodiamond or some other. I will talk about this later. You pick up this nanodiamond with a tip of AFM, place it on epitaxial silver, then you push a cube of silver, which would work as antenna, outcoupling antenna, so that it climbs the top of this single photon emitter. And by the way, nitrogen also has very good spin degree of freedom, which could be used as quantum memory. It's very good long coherence time, which you could excite with this microwave radiation and detect it optically. So anyway, in this case, what we obtained, this is work in progress. We already see 3,500 times decrease in the time of spontaneous emission. It means that the rate of spontaneous emission increased by 3,500. So that we obtained the lifetime as short as 23 picosecond, which is the shortest ever lifetime seen for nitrogen vacancy. And we proved that this is indeed a single photon source by doing these G2 function measurements. The trick, though, nitrogen vacancy is not a good single photon emitter. Because of coupling to phonon degrees of freedom, the broadening, the decoherence is huge. We don't want to beat the worst possible decoherence. We want to beat kind of modest decoherence. So the next step, which we're working now, we want to replace these nitrogen vacancies with germanium or silicon vacancies, where decoherence time at the range of 0.1 picosecond. So the spontaneous rate of emission is 1 nanosecond. I need to speed it up by 10,000. so that my photons would be emitted faster than 0.1 picosecond. And then they would outpace decoherence, and then they would be immune to decoherence. I think we are very close to this, and stay tuned. So we now just need to find out the good emitters, and I'm pretty much sure that eventually we will demonstrate it. First ever source of indistinguishable photon at room temperature. Nobody demonstrated it so far. That's absolutely critical for quantum information system. So yet another thing, I mentioned this spin degree of freedom in nitrogen could be used actually as quantum memory, which you could write, which you could control by microwave radiation. You, for example, could switch spin from 0 to 1 by applying microwave radiation. That would be like my flip from 1 to 0. And I could read it optically. The trick, though, when I read it optically, because fluorescence for S equals 0 system and S equals 1 system is different because of this non-radiative channel. By looking at fluorescence, which occurred slightly different frequencies, I could say whether it's spin 0 or 1. But the trick with this, you have to do it within the time shorter than this lifetime for this metastable state, which is 300 nanoseconds. Because if I do it too fast, too long, sorry, then eventually I move everything to S equals 0 system. It's an asymmetric system. You have to do it fast. So you would like to read your spin without changing spin. You have to do it within the time shorter than 300 nanoseconds. But the conventional rate of emission of single photons is 100 kilocounts per second. It means that within 300 nanoseconds, you have much fewer than one single photon. You cannot detect it. So the idea is, again, use this Purcell enhancement, this plasmonic structure, this confinement effect, to speed up the number of photons emitted per second, so that within one single shot, you would be able to read the spin system, your memory, without actually changing it. So that's yet another work in progress. And again, everything shows that we should be able to do it. So in principle, the whole idea of this plasmonic speed up, using this plasmonic materials, antennas, to speed up quantum processes, is eventually enable quantum information system operating at room temperature. Of course, that's very important. I demonstrated it for the case of the single photon sources, indistinguishable photons, but the same idea could be used for quantum frequency converter, for single photon detectors, and actually for deterministic gates. In all cases, because of the confinement, you make processes faster and therefore immune to decoherence. So that's kind of vision. That's the way we are trying to use these metamaterials to speed up quantum processes and make them immune to decoherence. So machine learning, I've already advertised. Actually, it makes a big difference for quantum photonics. We demonstrated it already for several things. I will show one that Sasha briefly mentioned yesterday, is specifically characterizing single photon emitters. Nobody did it so far, and we were amazed how it worked. And I should say this is remarkably talented young person, postdoc. Sasha challenged him, do machine learning for photonics for quantum, and he did it single-handedly. Absolutely genius young man. So how we do this single photon characterization? We do this anti-bunching experiment, same as Henbury-Brown twist experiment, well known. So you measure this, you use this correlation card and then measure the signal as a function of delay between these two arms. So, and normally you need to obtain the function like this as a function of delay between two the palms, this correlation, co-detection event, basically probability, and it has this dip. Normally, ideally, if it goes to 0, it is single photon sources. You always detect only one single photon, there or there. In reality, it never goes down to 0. And what people use is a rule of thumb. If it's below 0.5, this is single photon sources. If it's above 0.5, that's not a good single photon sources. So, but to get this anti-correlation function, you use this Levenberg-Marquardt fitting, which is given by this formula. To get the fitting, you have to have lots of data points here. You have to have like many meters measurement, collection time. Then you get good curve, you do this fit, then you take correlation function at delay equals 0. And as I said, if it's less than 0.5, it's a single photon emitter. If it's larger than 0.5, it's not a single photon emitter. But what if I mean, you have to pick up your single photon emitter out of thousands of different emitters. You don't know which one is really works. Thousands of them. What if I need to make thousands of single photon emitters? This approach simply would never work. For rapid device prototyping, for making quantum information cheap type of circuitry, you have really very fast characterization. And machine learning does really miracle here. If I use not minutes collection time, but let's say 1 minute, then that's how my spectrum looks like. There is no way to fit any function here like this. If you use like 1 second measurement, that's the way it looks like. I mean, how possibly you could identify this function there? Machine learning. You take many emitters, you pre-characterize them by doing this stupid long time consuming measurement, but then you train your neural network with many of them, and then machine learns and would say with very high fidelity whether it's single photon source or not. It's truly remarkably how it works. We were completely amazed. We use 5 different machine learning approaches existing. It turns out that convolutional neural network and this voting classifier works best. And let me just make the comment I made yesterday. Machine learning is a black box. Nobody knows how it works, why it works. It was developed for things like face recognition, voice recognition. The big challenge here, we need to develop machine learning, physics-driven machine learning for specific areas of physics, a completely untouched area. And it's hard to push this computer scientists to work in this direction. I don't know, they're lazy. I guess in the end we will do it ourselves, or we succeed in pushing them. So I would not go in detail how it works. In this case, you have this input layer, 3 hidden convolution layer, and this fully connected classification layer. And as for this voting classified, it has this logistic regression and k-nearest neighbor algorithm. So, but the results obtained are actually quite impressive. So the fidelity, which actually is the number of events when you predict correctly whether it's single photon source or not, to the total number of events, if you use this direct fitting, with collection time 1 second, you remember how spectra looks like. Basically, the fidelity is 50%, which means random guess, because you choose between single or not single. Of course, 50%, you always have this predictability. It means random guess. In other words, it doesn't work at all. With machine learning, we are around 80%. So it really works for spectra, which completely doesn't look like this, what you expect with long collection time. So we did both theory experiment. We just submitted this paper that's not even published. And for this very short collection time, which is needed, you need to characterize it fast, direct fitting absolutely doesn't work, meaning that the predictability around 50% of fidelity, whereas with this machine learning, you have around 70, 80% fidelity. So of course, it could be used not only for single photon characterization, it could be used for this characterization of memory, like optical reading memory. It could be used for this launching single photon into these antennas, for optimizing antennas. That's what we are doing now. We're trying to apply this machine learning to all components of photonic circuitry. And in parallel, we're trying to develop new machine learning algorithm specifically designed for these problems. And the first thing, very quick one, there is a very exciting area of topological photonics, which is, I mean, again, recent Nobel Prize, topological insulators. So you have a bulk, which is actually insulator, and you have only conducting edge state. Very exciting physics, and people try to mimic this phenomenon for photonic system, and that's so-called topological photonic insulators. And one of the, well, the pioneer in this area is actually, again, my friend Mori Segev. He demonstrated first photonic topological insulator in the optical range. But one of the most powerful approaches to do this photonic topological insulators was proposed by Hafizi from Quantum Institute, by the way, in Baltimore. What he suggested, this is the way the structure looks like. It consists of these units, 4 site resonators made of silicon. They resonate at 1.5 telecom. Every time light goes to this cavity, it stays there, high quality factor. They're connected through link resonators. Basically, it's like tunnels from this cavity to this waveguide and to this cavity and goes around. So the thing is, if we shift one of the link waveguides by zeta, so it's not symmetric. It turns out, as easy to show, if light propagates clockwise, which is equivalent to having spin up, and counterclockwise, which is same as having spin down, then actually the phase required would be different. And it's completely complete analog to what is called, to what is known Aharonov-Bohm phase. And that's applied for the well-known quantum Hall effect. In this case, you have an electron in magnetic field moving clockwise or counterclockwise, and the phase difference in this case exists. It's non-zero and depends on the magnetic field, and it's called Aharonov-Bohm phase. It enables all this beautiful physics, including this topological insulator, when you have this topologically protected H state. So in our case, in photonic system, we have exactly the same Hamiltonian. So photons described by exactly the same system. It's complete analog of this electronic system, but it's faster, it's photonic. And you have this, again, H states, which would be robust with respect to backscattering. Similar to electrons, you have this photonic H state. It's called photonic topological insulators. The thing to appreciate here, it's proportional to the shift, which depends on design, and refractive index. And I have a full control over refractive index. I hope I convince you with my presentation many things you could do with refractive index. You could switch it optically by other means in a very fast fashion. So that's a very attractive way. I could control the topology of my system, topological invariant, which is called Chern number, by changing the refractive index. Let me be more specific about this. This is normally how people characterize topological insulators, photonic or electronic for that matter, doesn't matter. This is a result of simulations. So you basically show this Aharonov-Bohm phase, which in our case played the role of synthetic magnetic field. Remember, this Aharonov-Bohm phase is proportional to the magnetic field. In our case, we don't have magnetic field, but this asymmetry works as magnetic field. It's like synthetic magnetic field. That's what breaks the symmetry. So you show this alpha as a function of frequency, and you have these band gaps. And within these band gaps, you have this a family. It's populated with these topologically protected states, which are robust with respect to backscattering. And the thing here, like, let's look at some of them. 0.45, that would be somewhere here. So that's a topologically protected state. You see it's H state propagated clockwise. It doesn't experience any backscattering. That's the beauty of this. If you take 0.5, it's topologically trivial. If you take 0.45, 55, sorry, you are here. And then you again have topologically protected. But this one propagates in the opposite direction, counterclockwise. So, but the thing here you have Chern number -1, here you have Chern number 1. You completely switch topological invariant, which is given by the Chern number. And I can do it optically by changing the refractive index. Again, if I change the refractive index so that I change my synthetic magnetic field, actually going from up to down, because that plays the role of the magnetic field, which reflected from the fact that Chern number becomes from negative to positive, I completely control my topological invariant. This is, again, idea of the same guy, Jacques Shalaev. I should give him all the credit. And to my knowledge, nobody suggested anything like this so far. And how you could control it, how you could actually switch this synthetic magnetic field. By changing refractive index. The simplest way, if you speak of silicon, we know that in silicon there is very strong thermo-optical effect. So we change the temperature, we change the refractive index. Refractive index depends on the temperature, and because of that, Aharonov-Bohm phase would depend on the temperature. To the extent I could switch the Chern number from +1 to -1. So we just combine this silicon waveguide with this titanium nitride heaters. And titanium nitride is stable, which can sustain at high temperatures. You apply power, and as our calculations show, is if power is 0, no heating at all, then Chern number is 1. If, let's say, power is 50 milliwatt, you change the temperature, change the refractive index, Chern number becomes -1. But you cannot, if you have the system with different Chern numbers, light cannot go from here to there. It's prohibited. That's why you have this H state. So, but now I could create, because here I apply this heat, here I don't apply this heat. Here I have Chern number +1, here -1. I force my light propagate along the interface between areas with different Chern numbers. I could do it this way, I could do it this way. I actually deterministically create virtual interface between systems with different topological symmetry. This is a kind of cool effect. And why it's important? Because we want to take it to the area of quantum. Quantum, everything is so precious. Now we're dealing with single photon or entangled photon. You really want to protect it. And topological insulators is the way to protect this quantum state. With this, let me stop. I tried to cover actually different areas which somehow related. They related, let's say, by our crazy curiosity. We would like to combine exciting physics with new materials and eventually bring into game-changing, world-changing applications. So we looked at this nonlinear optics enhanced by low linear effective index, this space-time metasurfaces, frequency array for ultra-fast beam steering, using the idea of plasmonic speedup to make quantum information system immune to decoherence and apply to this machine learning. Thank you, and sorry I took longer.
Quantum photonics and future applications. So we have time for a few questions from the audience. Yeah, back there.
False negative or false positive. What do you mean exactly that? It could go both directions. So what we do for that, we use these approaches which actually check your particular classifier. As I said, we check it against direct fitting trained. And when we check it, we see whether it's right or not. But it could go either way, plus or minus in that regard. We don't know. But we train our system, and then we look actually how well it works. And let me come back to the point I already made. How it works, why it works, we don't know. And the truth is, none of the computer scientists could have answer to this either. So we are not happy about this. We want to develop physics-driven machine learning algorithm. You could generate a relatively narrow band. Let's say if you want to take advantage of this area close to zero, epsilon close to zero. In fact, we would like it to be relatively broad band. People quite often ask the opposite question. So the area where it's really close to zero is relatively low. But it turns out that for these materials, which are Drude-like, it's not that narrow, and it's actually the broadest possible. To be specific, like 100 nanometer spectral range. So where you have epsilon really close to zero, like much less than 1. And that's the area where you have the largest enhancement. And if you would like to generate light, like white light or some harmonics, because this is a pretty much general nonlinear enhancement. The width would be actually dictated by the range where refractive index remains small. And roughly it would be something between 10 to 100 nanometers, depending on specific material.
Mark?
Right. So the time of steering is dictated by the difference in frequency, basically inverse of this delta omega. In terms of spacing between antennas, that actually eventually depends how broad angle you could cover. So, and that's actually completely depends on your design. In our case, it was 750 nanometers. So it's just a fraction of wavelengths if you're talking about 1.5. But in principle, you could control it. The closer the antennas, in principle, the better coverage would be, better sweeping. But the challenge, in this case, you would have to go below the diffraction limit. We use diffraction-controlled metasurfaces. Therefore, we're basically limited by the wavelength. And therefore, in our case, special separation is just a fraction of wavelength, let's say half the wavelength. But that works good enough. In principle, that's the direction to optimizing this system. Like in our case, it's minus 15 plus 15. You could make it a broad angle, and it's all doable. And one of the way of optimization is placing them tighter in space domain. That's a good point.
Question in the back.
Oh, the good news, overall momentum is conserved. So and I emphasize it. I mean, many people ask me this question. There are so many people they kind of guiding that nothing is wrong happening there. So nothing wrong is happening here because the momentum, what I break is photon momentum conservation. In other words, momentum for the photonic system. And I'm doing this through the modulation in space of my interface. So I introduce additional momentum through metasurface to which light couples. And that additional momentum breaks the photon momentum conservation. With conventional Fresnel's law, when it describes this refraction and reflection, interface does nothing in that regard. It doesn't break momentum, it doesn't break photon energy conservation. With my metasurfaces, I break both. If modulate in space domain, I introduce momentum and break photon momentum conservation. If modulate in time domain, then I break the photon energy conservation. So if I consider together metasurface and photonic system, both momentum and energy is conserved. But photonic system only, it's not anymore conserved.
I think we're at the end. Vlad, I have a quick question for you. So you talked a lot about generating single photons, indistinguishable single photons. Where do we need to be, where do you see the future of quantum communications, encrypted quantum communications? Where do we need to get to in terms of generating indistinguishable single photons?
I mean, it's a very, very good question. But for all quantum information system, quantum communication system based on optics, single photon source, it's like laser for all optical applications. Let's say this is a laser of single photons. Because eventually it's about this taking advantage of quantum superposition, quantum speed up. It's based on uniqueness of these quantum properties, quantum entanglement. If you don't have identical photons, you cannot create identical entangled pairs, and you cannot create a quantum superposition state. Let's say the brick for this building of quantum information system are identical, indistinguishable photons. If photons themselves are already different, no meaning in entangling them. It's not going to work. You have to have truly identical photons. And that's actually where the whole optical quantum information system and quantum communication starts from. And the truth is, as of now, there is no single demonstration of a distinguishable photon at room temperature. And with this approach, we hope to be able to accomplish it.
Yeah, fantastic. Okay, real quick.
I mean, efficiency, I told you, I mean, we have 500 million single photons per second. That's actually how many photons we get. And without this Purcell, it would be like 10 to the 5 photons per second. That's how you characterize a single photon. That's what the efficiency is about, how many single photons. But in terms of coherence and distinguishability, that's another characteristic. That's actually how fast are you than decoherence time. We are not there yet, but we're very close.
Excellent. Thank you. Thank you, Vlad. Wait. Don't go. So we're introducing, as the first distinguished lecture series. This may look familiar to you from other times, but it says Vladimir Shalaev, OU Research Distinguished Lecture Series, November 19th. Thank you so much.
Thank you, Thomas. So that's the thing. Thank you.
All right.
Thank you all, folks. Thanks.